So let's look at some examples of using this notation. So we'll write down a few matrices first. So I'll call A the matrix which consists of these entries. 2, 3, 4 is the first row, and then the second row will be 1, 1, 6. I'll let B be the matrix 1, 3, and 5, and then we'll call C the matrix consisting of those two entries, 3 and 6. So let's start with the dimensions. What are the dimensions of each of these matrices? Well, A has 2 rows and 3 columns, right? So that's the first thing we can say. A is a 2 by 3 matrix, and that's how you write it. Just write 2 and then kind of like a multiplication symbol. I mean, you're not going to actually multiply 2 and 3 and say that is equal to 6, although 6 is the number of entries you have, but you still write 2 by 3 because this is what shows the actual dimensions. B is 1 by 3, right? Because it has 1 row. And then C will be, well, how many rows are there? Well, there's 1 column only, right? 1 column, which is vertical, but then in each column, in each of the 1 columns, there's 2 rows. So C is a 2 by 1 matrix. So that's how we can write down the dimensions of those matrices. Let's pick off a couple of entries. Let's use this notation to reference some entries. How about we'll pick off an entry of A. So let's say I write down A and I put round brackets around it, and then I write the subscripts 1 and 3. So this stands for the entry of the matrix A, which is in the first row and the third column. So look at the first row and the third column, and then you see the entry that occupies those is 4. So that's all there is to it. And then if I write down, say, the matrix B, and then I pick off the 1, 2 entry, so the entry in the first row and the second column, well, there's only 1 row, so that first index better be 1, right? There's no other first index here that would make sense except 1, since there's only 1 row. But the second index could be 1, 2, or 3, and it is a 2 in this case, so we're going to take the second entry in the first row, so it's a 3. And then what about if I say the matrix C, and then I want to pick off the 1, 1 entry. So the entry that's in the first column, I should say the row first. It's in the first row and the first column. So first row, first column is going to be a 3. Just in case this isn't clear, let's do a couple more entries. How about the entry A, and then the indices will be 2, 3. So that's the entry in the second row and the third column. So there's 2 rows, so we're focused on the second row. And then the third column, we're going to look at the third column. So the second row and the third column, that gives you a 6. So this is equal to 6. And what if I wrote down the entry from the matrix A, which is in the third row and the first column? That's what this notation means. Technically this is valid notation if I want the entry of the matrix A, which is in the third row and the first column. But there's a problem here. That index is out of bounds. There is no third row for the matrix A, so this is just undefined. So is undefined. So that's how you can write down individual entries. A comment here. B is called a row matrix. You write that over here. B is a row matrix. You might be able to guess why. Just because if you look at it, it is a row. It consists of a single row, so it essentially just is a row. So that's why we say it's a row matrix. So I'm going to say that is, it consists of a single row. Okay, so I'm squeezing in the definition of a row matrix here. And you might be able to guess another definition is coming up momentarily. What about C? C is a type of matrix as well. It's called a column matrix because it consists of a single column. Let's write that down as well. So C is a column matrix. So in other words, it consists of a single column. All right, so we got that down now. A couple of remarks about matrices. One of the early things that comes up is you might want to look at a couple of matrices and decide, are these two matrices the same or not? And sometimes the answer will be yes, and sometimes the answer will be no. And I want to make two remarks on that idea. The first one is that the only way we'll ever allow two matrices to be equal is if, first and foremost, they have to have the same dimensions. That is a necessary condition. It doesn't automatically mean they're the same matrix if they have the same dimensions. Their entries could be different, but if their dimensions are not the same, we will immediately disqualify them from being the same, being equal matrices. So let's say this: matrices cannot be equal if their dimensions are different. Actually, I'll use the word distinct. That's a word that's commonly used in mathematics. It just means different, but it's got a really precise interpretation. You could think of points on a graph as being distinct if they have some distance apart from each other. That's kind of that's the imagery I always have in my mind when I use that word. But so to say that two objects are different objects is to say that they are distinct. So, okay, well, what if they do have the same dimensions? That's the second remark. The second remark is going to tell us how we can really quantify what it means for them to be the same. But first of all, they'd have to have the same dimensions. So let's say if A and B are both m by n. So if I'm writing that down, if A and B are both m by n, I'm really saying, okay, if A and B are both matrices that have the same dimensions and their dimensions happen to be m by n, in other words, m is the number of columns, m is the number of rows in both of these matrices, and n is the number of columns in both of these matrices. So if that's the case, then here's what it means for them to be equal. So A is equal to B, and we're going to say this really carefully. A is equal to B if and only if. So we're being very, very specific here. The only way these two matrices are equal is if the statement that I'm about to write down is exactly true. And here's how you can word it carefully. Really, if their dimensions are already assumed to be the same, the only way that they're going to be the same matrix is if all of their entries are identical. So in other words, for each row and column, so let's say for each I and j, and remember I and j have to fall in to very specific ranges, and I'm not just going to leave this be automatic in the background. I'm going to explicitly say it because this is an exercise in saying things precisely. So for each I and j with, well, I has to be between 1 and m to make sure that it's a suitable index for a row of both the matrices A and B, and j has to be a value between 1 and n to make sure it's a suitable index for a column. So for every single possible choice of indices I and j that satisfy the appropriate conditions, the corresponding entries are equal. So in other words, the entry from A, which occupies the ith row and the jth column, is equal to the entry in B, which occupies the ith row and the jth column. So that concludes that remark, and this tells you exactly what it means for two matrices to be equal. And if this statement fails to be true for a single index I or a single index j, it's automatically disqualified from being true in general, and the two matrices A and B would be distinct. But if all the entries are equal, then they are the same matrix. It may seem like I'm just wording it in a very complicated way for the sake of being complicated, but this is an exercise in using mathematical language carefully. So let's look at an example.